Hello, everybody. Welcome to Lecture 7 of Introduction to Data-Centric AI. Today, we're going to be talking about a pretty fun topic, large language models. We're going to talk about data curation and LLMs. So both data curation for LLMs and using LLMs for data curation. So show of hands, how many of you have heard about LLMs? Okay, almost everybody. And then how many of you have actually tried using one of these, say like GitHub Copilot or ChatGPT or one of the local models? Okay, awesome, like about half of you, maybe two-thirds of you. Great, so I'm gonna do some really quick background, but we'll get through this in a couple of minutes and then get into the details of data curation and LLMs. So at a high level, a language model is a sequence-to-sequence model that is trained to predict the next word or token in a sequence. So it models this probability distribution given prefix of a sentence or sequence of tokens. It'll tell you what the probability distribution is for whatever comes next. And that's a pretty simple model of what's going on here, right? And then the first L in LLMs is for large. So one thing that people have found is that increasing the model capacity, just having really high capacity models, and then training them on enormous data sets seems to give pretty interesting capabilities that don't really seem to be present at smaller scales. And so really the big innovation that's happened in the last several years is just scaling up. Oh, is that a question? Yeah. And what's super cool is that these large language models can be used to solve a variety of NLP tasks. They can be used as the foundation and kind of just doing a little bit of work on top, like not too much work and not too much like compute or expense. You can solve all sorts of interesting tasks. And so just some quick examples of applications of LLMs. One common application is zero-shot prompting. So these things have a really great kind of world understanding, lots of knowledge built into them. And so for certain tasks that you want to solve, you don't even need to do the whole traditional machine learning thing of like collect a data set and train a model. You just set up a prompt in the right way for the language model, give it the prompt, and it'll just give you back the answer. And so here's a concrete example. I just came up with this random example. Some time ago, I asked the language model to remove all the references to gender in a given sentence while retaining its original meaning. So notice there's not even a single input-output example, just a natural language explanation of the task I want the language model to solve. And on this particular example, the model does exactly what I wanted it to, right? Like it replaces she with they and her with their. So pretty cool that these language models have this kind of a capability. Another application you see of LLMs is something called few-shot prompting, or also talked about as in-context learning. And so here, it turns out that for some complicated, slightly more complicated applications, just describing what you want the language model to do and doing that zero-shot thing we saw on the previous slide is not quite good enough. But giving the LLM a couple examples of what you want it to do, some input-output pairs, that's enough to give you a high-quality result. And so here's an example where I actually didn't even specify directly in the prompt what I wanted the language model to do. I was kind of programming by example here. So here I wanted the language model to help me with a file renaming task and figure out the pattern. And so you can probably figure out the pattern by looking at the input-output examples. Like I have some file names with 1080p in them, and for those ones I want to strip that 1080p suffix and output JSON in this particular structure. Like maybe this is feeding into some program that actually does the action on my file system. Right, so I gave a couple examples like this one, I rename this to this thing with this 1080p stripped, but okay, maybe for the 720p things, I want to delete them. So I want this kind of an output. And so I just give a couple input-output pairs, and then I say, okay, given this, now give me the output corresponding to an unseen input. And turns out this works. And here it's pretty clear that if I didn't give these examples, I just wouldn't get a sensible result, right? Like I haven't even said enough in the initial prompt. Yeah, okay, so you're pointing out that in these examples, it's always the case that the ones that start with one are delete and the ones that don't start with one are not delete. And so, that's a good question. I think to some degree, we can't fully explain exactly how these language models work, what their internal understanding of the world is and how they're producing the result they're producing. It's more like, I think the way people think about it is it's just like it's behavior that the system has, and we're going to experiment with it and see what we can do. And so, yeah, I think there's no way to tell, maybe besides giving a bunch more input-output examples and seeing if it breaks down. Yeah. Yeah, but they're kind of, I think fundamentally, if you're doing programming by example, and you have a limited number of input-output pairs, there's more than one function that maps all the inputs to the outputs correctly, and it's an underspecified problem. But here, it's not like we're even getting a kind of encoding of the mapping. Like if we ask the language model maybe to produce a Python program that does this, we might actually see what program it produces, and that's a more interpretable result, and that's one way we might go about it. But if you just ask it to produce the output, it's kind of hard to tell how exactly it's computing that. Maybe it's doing the right thing, maybe it's not. Does it even matter if it produces the right output? Yeah, any other questions here before we move on? All right, yeah, so that was, one more background slide. And so we talked about zero-shot prompting, like just give a natural language description of your question, get an answer out, works for some tasks. If you want to solve more sophisticated problems than that, this technique of few-shot prompting can be adequate to solve the problem. And there are a couple other applications that LLMs are commonly used for. One is called, here in the slide, it's retrieval augmented few-shot prompting. You might have heard the term retrieval augmented generation, or RAG. And in this application, consider, like, okay, so these LLMs are trained on these huge text corpuses, things like just internet scraping and Wikipedia and like OCRs of books and things like that. And so they have pretty good kind of understanding of the world and kind of public information. But suppose you wanted to, say, you wanted to build a system for searching your company's internal documents. Like maybe I have 100,000 documents in my company's Google Drive, and it'd be super cool if people could query those using natural language, right? And be like, oh, like, tell me this thing about this system we've built, and it'll understand the documents and give me a good response like LLMs can do. Except you can't take an LLM, it's one of the kind of off-the-shelf ones that are trained on public data, and uses zero-shot prompting or few-shot prompting for that task, right? Because the LLM just has no knowledge of your company's internal database of 100,000 Google Drive documents. And so what people do in RAG is they combine a retrieval system with the LLM. So given a query, you will look up in a database of documents formatted appropriately, what are the most relevant snippets, and then all that gets fed into the LLM along with your query, which then is used to generate the final response. So yeah, no need to understand all the details there. That's just one other application of LLMs. And then finally, LLMs can be fine-tuned. So you might have heard about fine-tuning, say, in the undergraduate machine learning course that you took. Maybe you trained an image classifier, starting with, say, an ImageNet classifier, and you trained it, you fine-tuned it on your own image classification problem. So fine-tuning is starting with, say, an existing neural network, and then maybe making some small tweaks to the structure of the network, and then adapting it to a different data set, right? And so fine-tuning often gives the best results with the LLMs. If you want to train the model to solve a particular task, and you have a bunch of input-output examples, it actually works better than few-shot prompting, actually updating the weights of the network. And so these are 4 things that are commonly done with LLMs. From left to right, they go in increasing order of like amount of effort, right? Zero-shot prompting, you can do that in 1 second. Few-shot prompting, maybe you need like 3 data points. That takes a little bit more effort. Whereas fine-tuning, like now you need to collect, say, a couple hundred or 1,000 data points, and then actually fine-tune your model. So you're going to need like a GPU, and it takes a couple hours to train the model. But still, even at the fine-tuning level of complexity and effort, it's still, the compute costs are kind of on the order of like hundreds or thousands of dollars, not kind of millions of dollars, which is the cost of training an LLM from scratch, like that base model that's pre-trained on a huge text corpus. All right, so that's it for the rapid background on LLMs. So in this lecture, we'll talk a little bit about using LLMs for data curation. So this, the general theme of this course, like how do we approach data collection and curation in a systematic way? LLMs can be used to help us with that task. If we just want to have a high quality data set, it's a useful tool. We'll also talk about how to evaluate the outputs of LLMs, because that is another type of data, and evaluating those outputs can be helpful for various purposes. And then we'll talk about the flip side. We'll talk about how to curate data used for training LLMs. And these things kind of combine, like you can use some of the techniques that are used in LLMs for data curation in order to curate the data that you're then going to feed into an LLM training pipeline. So we'll talk a little bit about data curation for pre-training the LLM-based models, but not spend too much time on that, just because I think like most of us probably aren't going to be training one of these models that cost millions of dollars to train. Whereas these LLM applications, like they're so accessible that I think it's really likely that a lot of you are going to do, say, LLM fine-tuning at some point. So large language models are really powerful natural language reasoning engines. And as we've seen in those couple of examples earlier, they're really easy to customize for new use cases, right? You have some particular natural language related task, and within kind of seconds or minutes of effort, you can get pretty good results on that task. And it's inexpensive in terms of time you spend, and also computationally pretty inexpensive. And so this is revolutionizing the way we go about doing data curation for text data sets. And so let's look at a couple examples to make this really concrete. And basically, there's a bunch of data curation tasks that fit really well into the set of things that LLMs can do. So one thing that you might want to do is avoid training an ML model on data containing personally identifiable information. And there are a number of reasons why you might want to do this. One reason is that a machine learning model can actually leak its training data, like it to some degree like memorizes or understands its training data, and there are ways to kind of retrieve that training data out from the LLM. So if you train a machine learning model on private data and then, like, say, expose it to the world or give the model out to people, it can be a privacy issue. So that's one reason why you might want to remove PII from a training data set. And so you need to detect it. And then, kind of curious what people think. How exactly would you handle, say, presence of PII in a data set that you're training on? So you have a medical data set and it happens to contain, say, like people's names or certain sensitive things. You want to get rid of that. You want to keep the non-personal stuff, medical conditions or other things. So what could be tricky about, how would you address PI in a data set, or what challenges might arise? Any ideas? Yeah. Yeah, absolutely. So we'll talk about that in a moment. That's for how we might be able to scrub PII. But one note about how PII could be handled or should be handled, it's not always just as straightforward as like detect it and say throw away the data points containing PII, or detect, say, like all the names and just replace them with like dash, dash, dash. Because in certain cases, like suppose you have a text data set that's talking about different people, and individual data points talk about multiple people. So you have, say, like Anish mentioned in that data point, but also like Curtis is mentioned in that same data point. Maybe that single data point is like a conversation that the two of us had. If you just scrub all the names out, you've lost the context of like speaker one said something, then speaker two said something else, then speaker one replied to that. It's kind of that, like those correlations are lost. And so that's one example of a case in which you have to be careful. Like if you're dealing with that kind of a data set, you might want to identify the PII and then do some kind of like deterministic replacement of, okay, the first name you find, replace it with speaker one. Second name you find, replace it with speaker two, but keep this consistent. So in the past, the way people dealt with PII was in a somewhat manual way by thinking about all the different types of PII that might appear in a data set and like writing regexes to find that sort of thing. So here's some screenshots of code from this scrub-a-dub library. It's a Python library, a bunch of people use it. And you can see how it implements some of these features. Like it can detect credit card numbers, or it can detect Twitter handles. And like somebody had to think about this and write down like, okay, here are the rules for how credit card numbers can be formatted, or here are the rules for how Twitter handles can be formatted. And so what are the downsides with doing PII detection this way? Any ideas? I think of a bunch of them. Yeah, that's a really good one. Like here you have to explicitly enumerate all the different types of PII and make sure you haven't missed anything, right? That's a lot of hard work. And then yes, separately from that, just writing these regexes is a lot of hard work. Like if I asked you to do this, you'd spend hours and hours thinking through all the different types of PII and writing these carefully written regexes. Whereas now with large language models, you can do this in like 1 second instead of hours and hours of work. And you don't even need to think about all the possible types of PII because the language model has a pretty good understanding of what PII is. And so here's an example of a prompt I wrote. to detect PII in text. I said, consider the following product review. Yeah, so this is specialized to an imaginary data set that I had in mind of product reviews. And I say, consider the following product review, and then here's where I'm going to inject the text. So if I have a big data set, I'll run this prompt one time for each of the data points, injecting in the text here. And then I have this prompt for the LLM saying, okay, tell me whether or not this has PII in it. And then prompting LLMs is a bit of an art. There's tons and tons of papers on the topic, tons of blog posts. We're not going to go into details on like what's the best way to prompt LLMs. But yeah, here's just one example of how I prompted it. And I wanted it to output a final judgment, like output : true or output : false, if the example contains PII. And so you could imagine how this could be used if I had, say, an API key for OpenAI, and I could run my data points through there and then get the response, and then parse the output and see if it contains this output true or output false at the end, and then say I could drop data points if they contain PII. Maybe I want to do that in my particular example. So it turns out like this prompt works pretty well. Here are some examples. Like I say, okay, I'm a professional wildlife photographer. I've been shooting with this camera for 6 months. It's been amazing. Example product review. And then the LLM says, okay, this has no PII. Right? So pretty cool that it's solving this problem that these scrub-it-up people had to put in a lot of work to solve with very little work on our part, right? And then just here's a positive example. I mentioned a name in here, and indeed the output says true. And what's kind of cool is that, okay, here's an example that has a type of PII in it that's not explicitly enumerated in the prompt. So I've said, find PII that includes but is not limited to PII such as name, location, or credit card number. Be sure to catch PII not listed here. And so it's kind of cool that it's able to figure out, like, yeah, even though this thing isn't formatted like a name would be formatted, if you imagine like the scrub-it-up Python library having some sort of regex pattern for names, this wouldn't be caught, right? They need something specially for Instagram handles. But yeah, this prompt, even without explicitly mentioning it, is good enough to catch this piece of PII. Yeah. Yeah, so the question is, has this been deployed and used on real data sets? I think it depends. The cost doesn't have to be that high. There are also tricks you can use, like you can batch multiple data points in single query so you don't repeat the prompt or things like that. For some of these questions, like the PII one is pretty basic. You probably don't need the super powerful GPT-4 model. You can just use like GPT-3 or something. It's a lot cheaper, or some of the local LLMs might handle it too. So yeah, absolutely, it is being used in certain places. Yeah.
So will they also be used in other places? Because I think OpenAI has not made it clear that by using the API or we just input the data containing API will not be reused for training. Would that be a concern?
Yeah, so the question is, if you're using an external API, maybe you don't want to send a data that might potentially contain PII to this external API in the first place? Yeah, that's a good question. So yeah, I think in cases like that, one option is just to run an LLM on your own infrastructure. Like there are plenty of open source ones that you can just run yourself. There are other setups now, like AWS Bedrock, for example, where you can run, say, like an Anthropic LLM, but within AWS infrastructure, and you have kind of all the security guarantees of AWS. Yeah. Yeah, so the question is, have we seen people use commercial APIs or self-hosted ones? Both. Plenty of people have data sets that are not that sensitive. Okay, like I think maybe for this PII example, you don't want to send it outside. But one other example that we've done is finding, say, grammatically incorrect text or informally written text or stuff like that. And we've talked to people who are, say, analyzing social media data sets and they want to throw out all like badly written text. And so that's all public information anyways. And so it's totally fine to use an API for that. Yeah. Yeah, that's a great question. Is there a way to get some kind of a confidence score from ChatGPT? Maybe it's going to make mistakes and say the wrong thing, say output equals false in this case. And yeah, how do we handle that? That's a really great question. I'm going to talk about that later in this lecture. But yeah, absolutely, it's a hard problem, and we have some ideas for how we might be able to solve it. Any other questions here? Okay, so yeah, this is a complete example of how we might solve just a classic data curation problem using LLMs as a tool, right? And using this zero-shot prompting technique. Just as one more example, we can go through this one a little bit quicker, illustrating one of the other ways of using an LLM. Let's talk about checking grammar. And so the old approach of doing this was classical NLP and hand design lists of rules. And this stuff is actually used, like here's a screenshot from the language tool library, which is used in OpenOffice, among other places. And yeah, don't try to like understand the code. It's some XML from a big rule list. But yeah, basically some people had to like sit down and think very hard about what kinds of patterns appear in text commonly and are grammatically incorrect, right? That's a ton of work to do. Like actually, it's not just writing down examples of bad grammar. You actually have to write down the rule that describes like, the bad grammar in a general way. And so yeah, really tricky to do and a ton of work. But one way you can solve this today by building on top of large language models is, yeah, in this example, we'll utilize fine tuning. I think this might work out okay with, say, zero-shot prompting as well. But let's just talk through how we might do this with fine tuning. One thing you could do is collect a data set of sentences, collect a big corpus from the internet, and then have people judge whether or not those sentences are grammatically correct. And so now you have a bunch of examples of input-output pairs, right? So now it's just like a classic supervised learning problem. And notice that this is a much easier task than manually writing down the rules, right? I don't think I could do this, but I don't know, I think I have pretty decent grammatical skills. Like I can probably decide whether or not a sentence is grammatically correct. And like some people have indeed done this, for example, like there's this corpus of linguistic acceptability that you just download, so you don't even have to do this work yourself. And then what we can do is we can fine tune a base LLM, so one that already has an understanding of English language and an understanding of the world and so on this data set. And yeah, notice that this is not a sequence-to-sequence task anymore. Like we're not trying to generate text. We're trying to just classify, like, is this sentence grammatically correct or not? But yeah, pretty standard thing to do with an LLM. And these days, given the high-quality open source libraries that are out there, it's literally just a couple lines of code. Like you use Hugging Face transformers, write a couple lines of code, have like one GPU, and like 1 hour later, you have a model that solves the problem. So any questions there? All right, yeah, so now we're gonna address your question. A major challenge in working with these large language models is something people refer to nowadays as hallucinations. They produce outputs and you can't really tell whether the output is good or not, or there's no kind of built-in way of telling whether the output is good or not. Sometimes you can get outputs that kind of look reasonable at a high level and yet are incorrect. And so here's one concrete example of that. I asked ChatGPT or GPT 3.5, what is 38 plus 72? And it gave me the correct answer. And then I asked it a different math problem. What is this number times this number? And it gave me this response. And it's actually just wrong, right? So if you didn't want to do the math yourself and you were just looking at these answers, like how are you going to tell these two things apart? It's kind of a hard problem, right? Now, if you imagine, say, using this for that data curation task we were just talking about, maybe you incorrectly flag things as PII when they're not PII or vice versa, and now you're throwing away like the wrong data points. And so this is a real challenge. And so how is this addressed? I'll talk about two techniques. One technique you can use is use a more powerful LLM to evaluate the outputs of a weaker LLM. So as one concrete example, as I was preparing these lecture slides, so yeah, playing around with ChatGPT to get all these examples, and going back to that PII and product reviews example, I tried putting in this text here, and then this prompt is slightly different. It's an older version of the prompt that had a little bit less of that, like explain your reasoning, chain of thought style prompting, and I just asked for the answer. And turns out, like, I guess this prompt and this data point didn't work out super well. So yeah, I just got false back as a response, right? So it's just an incorrect answer. But what's kind of interesting is then I use GPT-4, which is a much more powerful LLM. And then I haven't shown the full prompt here, but there's a prompt that says, like, okay, you're given a query and also an output that's generated by some other LLM. Like here's a scoring criteria, score how well that output answers or the query given in the input. And so, yeah, that's up here. Some of it's hidden. But then I gave, just copy pasted my input and output into here. And it turns out that GPT-4 is able to reason about this and say that this given answer is incorrect. And so it scores it lowly, and it scores it as like a 1 out of 5, like low quality response, and even explains what's wrong with it, that, okay, there's an Instagram handle in there. So this is one technique that you can use. And this general idea of using LLMs to evaluate the results of LLMs is actually quite commonly used in research. Like people develop some sort of NLP system, and then they'll want to evaluate it, right? And like, how do you evaluate an NLP system? Maybe you could have a bunch of humans do it, or if you want an automated evaluation, and it's not just like, say, a classification problem where you already have a test data set, it's some sort of like text generation problem where it's a little bit harder to automatically score the outputs. People often just use more powerful language models to judge the weaker ones. It's a kind of, interesting pattern that people commonly use. Does anybody see any issues with this?
Why don't we just put the information in questions and more powerful GPT-4 in the first place?
Yeah, so that's a great question. It's like, okay, if we have GPT-4, why are we using GPT 3.5? Why not just ask your question to GPT-4 in the first place? So that's a good question. One reason to use weaker language models is that they're cheaper. Like if you just look at OpenAI's pricing, for example, the rate limits are much higher for GPT 3.5 and the costs are lower. Though if you do need to feed every single data point through the bigger language model anyways, it's not just for, say, like evaluation purposes before deployment or something like that, then yes, in that scenario, you might as well use the larger language model. Yeah. Yeah, exactly. So, depending on the use case, if you're just using the more powerful language model for your task, like, this doesn't work anymore for evaluating it. Like, it's probably going to agree with itself. So, actually, I forgot about this slide. Before we move on to talking about the problems with this, I'll talk about where it can be effective. So, tons of neat results out there. Here's one of them. There's this Alpagasys paper where the authors fine-tuned alpaca on a curated data set. Okay, so a little bit of history here. Llama is an open source large language model developed by Meta, and then Alpaca is a project done by Stanford where they fine-tuned this base Llama model on a bunch of synthetic data points, and those synthetic data points were like instruction following data points. And so it resulted in an instruction-tuned model that's better for this like zero-shot prompting. And so Alpaca was fine-tuned on these 52K synthetic data points, but these authors, what they did was they took those 52K synthetic data points and then noticed, like, there are actually a bunch of issues in this data, right? General theme in this course, like, if data has issues, your downstream results are not going to be quite as good. So they found a bunch of issues in them and actually used GPT 3.5 to score or evaluate those 52K data points, filtered out the best 9,000 of them, and then instead of fine-tuning Llama on the big data set, they fine-tuned it on the high-quality small data set. And I haven't included the full evaluation results here, but at a high level, like the resulting model significantly outperformed the base Llama model. And here you'll notice this, like, okay, they evaluated that using GPT-4, which is kind of interesting, but also did a human study. So this pattern of using powerful language models to evaluate data can be quite useful in certain scenarios. But going back to this question of what happens if you want to evaluate the output from your powerful large language model? So that's totally, is it turtles all the way down? What if you're using the powerful language model in the first place? So we'll talk about a technique we can use in that scenario. And then I also just wanted to flag that this method of using the more powerful language model obviously is not foolproof. So going back to the arithmetic example from earlier, the incorrect one that I showed you, I gave that same input-output pair to GPT-4, this was originally generated by GPT 3.5. And then here, GPT-4 says, the response written from an AI assistance perspective, blah, 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 there's no room for improvement, and in this case, the answer fully and correctly addresses the user's instruction. This is like the text says it's very confident about the result. It scores it a 5 out of 5. But we know that this is wrong. Any questions so far? Yeah. Yeah, that's a good question. So what happens if you use just a different model, perhaps trained on a different data set or different architecture to evaluate, like a Google model to evaluate GPT 3.5? I think you can find papers with big tables of like using this model to evaluate that model. I think at a high level, people have a sense of which language models are more powerful than others. There's kind of an ordering. But then to some degree, there's people also know like which language models are better for tasks in certain domains because they're all trained on slightly different data sets. And so I think it just like it depends on what the task is that you're evaluating it on and which model is better for that task. Yeah. Yeah, that's a great question. Is there like, can OpenAI just detect that you're trying to solve a math problem, and can the language model call out to a calculator? And so, like, absolutely, they've built this. Yeah. 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 So the question is, can you generate several outputs from a language model, and then what would you do with those several outputs? Yeah. Yeah. So can we use the strategy? Yeah. Mm-hmm. Yeah. Yeah, so that's great intuition. And actually, we can even simplify things a bit because if you think back to Jonas's lecture with multiple annotators, there we had the setting where some annotators were better than others. Like maybe multiple doctors, and some doctors are just better than others, or they have like a medical specialty or something. Whereas here, if we prompt the LLM multiple times, like it's just the same LLM. Maybe the LLM is usually operated in a non-deterministic way, so it'll just produce a different output every time randomly. But it's not like it's just kind of the same LLM, and you'd expect one answer to be just as good as the other. And so you can actually simplify. You don't need the full complexity of what Jonas presented to deal with that scenario. And so, yeah, that actually leads nicely into the next slide. Like here, I'm presenting one idea for how you can quantify the uncertainty of LLMs, kind of get around this issue we saw on the previous slide of like how do you evaluate the powerful language model. And it actually uses this idea you were just talking about, where you prompt the LLM multiple times and then do something with the results, treating it kind of like a multi-annotator problem. And so, yeah, Jonas is actually one of the co-authors of this paper. And here I'll walk you through the technique. The high-level idea is pretty intuitive. And so there are two pieces to this that contribute to a final score. And so we start off with just the base input or question to the LLM and get an answer. And then we have two scores, an observed consistency score and a self-reflection certainty score. And so the observed consistency is basically what you were just talking about. So you prompt the LLM multiple times. There are a variety of techniques you can use to try to get slightly different outputs every time. One is, say, like varying the temperature parameter to the LLM to get like more diverse output, or you can also try tweaking the prompts a little bit. But what you do is you get a number of outputs for the same question, and then you compare those all back with the kind of original response that you're going to give or that you want to score. And so and then the way we want to compare those is obviously not something like, are these identical, the same string, right? Because these things are generating text, things might look a little bit different. But what we can do is use a natural language inference model. So yet another machine learning model that's trained to do a slightly simpler task, which is take in two pieces of text and determine whether or not they contradict each other and give a score associated with that. And so we can run this NLI model on on the original answer paired with the first example answer we generated, the second one, and so on. And we get a whole bunch of scores there, and then we can average those things, and that gives us one component of a final score, right? And just intuitively, if the LLM is uncertain about the answer, you might expect that it's going to produce like just a bunch of different looking answers, right? Like the math problem I gave it earlier, maybe it'll just give a bunch of like kind of random numbers that are roughly in the right range, but it's not really doing computation correctly, so it's not going to consistently give the same answer. Whereas if it's certain about the answer, maybe I'll just see the same thing every time. And then another interesting thing you can do is, it turns out that if you give back to the LLM the original prompt and the response that you got back previously from the LLM, and then ask it to reason about its own answer, that can also be a helpful signal in
determining whether or not the LLM is certain in its output. So you can actually set up just a zero-shot type of prompt, which is here's a question and answer. Like explain the reasoning that gets you to this answer, and then decide whether or not you think the answer is correct or incorrect, or if you're not sure. And so, yeah, none of the, like, unlike some of the techniques we talked about earlier in the course, like the confident learning stuff, none of this has like formal proofs backing why it works. I think a lot of the research right now related to large language models is very heuristic, and you come up with some ideas that seem intuitively reasonable, and then you very thoroughly benchmark them on a bunch of examples. And so we're not covering the benchmarking aspect in the lecture, but if you want to, I'll share the lecture slides later, and then this is a link to the paper. And you can see that, yeah, like this indeed gives you like high confidence scores when the answer is correct, and in situations where the answer is incorrect, lower confidence scores. And so we have benchmarks that show that this works pretty well. And so yeah, this is a conceptually simple technique you can use to determine the confidence of LLM outputs. And then this can factor into whatever you're doing downstream. And the way you actually handle that confidence score will just depend on the actual task you're using the LLM for. Yeah. Yeah. Yeah, so this is we have an implementation of this. Just one concrete example. Maybe the text is a bit small to read. I asked it, who was the first author of the Attention is All You Need paper? And it gave me a correct answer. The first author is, and then it gave me his name. Confidence 91.44%. And then I asked another question about a different research paper. I'm not sure if this was in the training corpus or not, but I asked, okay, what programming language was used to implement the search engine in this paper? And then the language model answers, the paper doesn't explicitly mention the programming language used to implement the search engine. So I've read this paper, this answer is wrong. But what's kind of interesting here is that, yeah, this confidence score is actually lower, right? So it's kind of nice to see this correlation between, wrong answers have lower confidence scores. Any questions there? Well, so moving on to the next topic, let's talk just briefly about data curation that goes into training the base LLM. So this is something that, I think the people in this class are maybe less likely to do because it's just something that requires so many, such compute resources and such a big data set, whereas the other applications we talked about, I think, very likely that you'll all work on those. But let's briefly talk about this. So what I'm showing here is a screenshot from the blog of an OpenAI researcher. You don't need to read all of the text, but I've highlighted the key part. He says that LLM model behavior is not determined by architecture, hyperparameters, or optimizer choices, not by the modeling side of the problem. It's determined by your data set and nothing else. And so this is consistent with the themes of this class, right? Even in the LLM application domain, it seems that, the details of the modeling don't really matter that much, or don't matter nearly as much as the data and the data quality. And so what goes into the data quality for these large pre-trained models? Well, here are just a couple of the ideas. There's tons and tons of research on this. Obviously, we don't have time to get into the details. But some of the key ideas used in training systems like GPT 3.5. One is just the first step of training these language models. Recall that they're just trying to, what you're training them to do is given a sequence of text, predict the next token in the sequence, right? And so how you start out is just get tons and tons of text and do unsupervised pre-training on that text. And then researchers have noted that even here, the quality of this corpus matters. It's very hard to get an LLM to unlearn something. So for example, if you have things that look like factual statements that are actually just wrong in your training corpus, then that's going to be problematic because you can't get the LLM to forget that behavior later. And then these corpuses come from places like, you might use all of Wikipedia, or you might use OCRs of books, or you might just scrape the internet and download all of Reddit and use that. Then you have to be really careful. And all of the data quality, data curation ideas we talked about earlier in this course are all relevant here. And then for the more recent LLMs, some ideas that have gone into improving their performance include supervised fine-tuning. So once you do this base training over your big data set, what you do is you have humans just write down a bunch of good input-output examples. And then it's much more like a classic supervised learning problem. You do supervised fine-tuning of the model. And then you've probably all heard of this RLHF, reinforcement learning from human feedback idea. This is one thing that went into GPT 3.5 or ChatGPT.
And at a high level, what they did there was they wanted to train their model to produce high quality outputs. And you can frame that as a reinforcement learning problem. And you could imagine having a reward function that's a bunch of humans scoring the output of the language model. Like in your reinforcement learning inner loop, like your language model's producing outputs, humans rate the outputs, and that feeds back into training the model. Except that would be really expensive to do because you need humans to rate tons and tons and tons of outputs. So the trick that they played here was that they had humans giving feedback on a smaller number of data points, and then they trained another machine learning model to kind of emulate the human's behavior. Like given the inputs and outputs of an LLM, give it a score, like rate it, how good it is. And then they use that as the reward signal in a reinforcement learning setup to improve the base LLM itself. Yeah. Yeah, that's a good question. Can you do something similar for the supervised fine-tuning step and produce more input-output pairs using automation? Yeah, so absolutely. There's some neat papers that... Yeah, so I think one tricky thing is, I'm not sure you can use that, or you can even use that to improve, like use an LLM to improve itself, which is kind of cool. But one other thing that's more obviously like a reasonable thing to do is you can kind of distill or use a large LLM to train a smaller one by using the large one to generate these high-quality input-output examples. And so there, yeah, I think I might have a link somewhere in the slides, but there are examples of people, yeah, training a model that's much smaller than OpenAI's GPT models, designed for a specific task, and then all the like 100% of the supervised fine-tuning training data for that came from the like GPT 3.5 or GPT 4. Any other questions here? Yeah. And this is a huge topic. This is like a 5-minute or 1-minute overview. There's tons and tons of research on how to do better training for these base LLMs. What I think is a little bit more interesting to talk about in the scope of this class is data curation for these applications of LLMs. Like once you have the base model and you want to do something with that. And data is relevant in almost all of these applications. Maybe a little bit less so in zero shot, in that the only thing that goes into that is the prompt engineering. I don't know if you consider that data or not, but clearly in few shot, where you have a prompt that you've tuned plus a couple input-output examples, like turns out that the quality, pretty obviously, the quality of those input-output examples is crucial in getting good performance and stable performance from the LLM. So if you're interested in more of the like science and benchmarks there's a link to a paper here. Then clearly in RAG, like you have a database of documents that you're using to help feed into your generation. The quality there is going to matter. And then finally, supervised fine-tuning. If your input-output pairs are better, you're going to get better results. And so let's spend the last couple of minutes talking a little bit more about this fine-tuning step. So why would you want to do fine-tuning? It gives the best results for some specific task that you want to solve. And what's kind of interesting here is that a common paradigm to use is you start with some small kind of manually curated data set, and then you use an LLM to generate more data for fine-tuning. So does anybody have any ideas why you might want to do this? Or like, does this even make sense? Would it make sense to use GPT-4 to generate more data to feed into GPT-4? So one thing that's commonly done is people want to fine-tune a smaller LLM for a specific task. And this is because smaller LLMs are cheaper. There can actually be a huge difference in cost, both in terms of like how long it takes to do inference and the actual dollar cost of that inference. And so it turns out that you can do this, and it's helpful to use the more powerful LLMs to generate the training data for these smaller LLMs. And so at a high level, the process looks something like this to do synthetic data generation and data curation for fine-tuning. So you start out with some original data set, like you need some input-output examples that you've created yourself, and you want to first just improve the quality of that base data set. And so for that, you can use all the techniques we've taught earlier in this course. And then the next step after that is to generate synthetic data using a powerful LLM. And using some of the techniques we talked about earlier in this lecture, you can quantify the quality of the output, and maybe you can do something like throw away the outputs that you think are not very good. And just to make it really concrete, like how do you get LLMs to generate synthetic data? The way you do most things with LLMs is like by feeding them a prompt string, right? So here's an example of, this is the actual prompt used to create that synthetic training data set, the instruction fine-tuning data set that was used to train the Stanford alpaca model. So yeah, this was just fed into, I don't remember exactly which model, maybe GPT 3.5. Like, you were asked to come up with a set of 20 diverse test instructions, blah, blah, and they go on to say what else they want in terms of requirements from the LLM. And this gives you your synthetic data. Any questions so far? And then after that, so now we have our cleaned base data set. We have some synthetic data. And then the step we want to follow next is to filter out the bad synthetic data from this data set. And so one thing we might do is look at the entire data set, right? We have a mix of synthetic and non-synthetic data. And we could train a real data versus synthetic data, just a binary classifier on that data, and use that classifier scores to toss out the examples that are unrealistic. So this will give us a higher quality data set. Then we can go back to our what we did in the first step, which is just applying these general data cleaning principles and practices to the full data set of original plus high quality synthetic examples. And then finally, we can take that data set and use that for fine tuning and get a high quality model out at the end of the day. So yeah, this is the recipe that we recommend. Any questions there? And I'll end this lecture with just some brief thoughts on the future of data curation, especially with where we're headed with foundation models. So, if you haven't heard the term before, people use LLMs and foundation models kind of interchangeably, but just think large models trained in an unsupervised way on large chunks of data. So today we have powerful multimodal LLMs. So we don't have these just for text, but we have models that can understand images, for example. You can do this today with GPT-4. And so what we used to have to do with, say, Python code we wrote, like we had this package called Clean Vision that could find a bunch of issues in image data. Like, okay, you have a big data set. Here's an actual image from ImageNet, by the way. And one of the things you might want to do is find like the really dark images or light images or blurry images or something like that. And before, in order to do that, we had to write Python code that implemented like basically classical computer vision algorithms to identify those issues. But now you just like GPT-4 can just solve this problem in a zero-shot way. I just gave this image to GPT-4, said, score its darkness on a scale of 0 to 1, and I got a pretty reasonable response. And so I think these foundation models will come to solve a lot of these data curation tasks in the future. All right, so that's all I have for today. Any final questions? All right, and then a quick announcement. This is actually the last lecture for this course. I'll update the website later, but we'll be putting the slides and the videos and all the lab assignments online. But no lecture this Thursday and Friday. Hope you all enjoyed the course, and then we'll continue to answer questions on Piazza and email if you have any final questions. Well, thanks everybody.